In these tutorials, we are going to talk about the modulus, argument, and principal value of argument of a complex number. Now, before we start, let's briefly talk about the argand diagram. Now, complex numbers can be represented on the Cartesian plane like this, where the x-axis will represent the real axis and the y-axis will represent the imaginary axis. Now, assuming you have this complex number z equals a plus bi, when you are representing it on the Cartesian plane like this, like I said in the earlier videos, we can plot complex numbers, or we can write them in a coordinate form like this, where the a part represents the real part and the b part represents the imaginary part. So we can plot this on this diagram. So here we are going to get something like this. So a comma b will be here. Alright, now when we plot complex numbers on the Cartesian plane like this, we call this the argand diagram. The argand diagram. Argand diagram. Okay, that was just by the way. Now let's move on to the modulus of a complex number. The modulus. Now the modulus R of a complex number z equals a plus bi is written as absolute value of z, which is defined as the square root of the sum of both the real part and the imaginary part, a squared plus b squared. So this is how we find the modulus of a complex number. We find the square root of the sum of the squares of the real part and the imaginary part, and it is written as the absolute value of that particular complex number. So when we have complex number omega equals c plus di, the modulus of omega, which is absolute value of omega, is going to be square root of c squared plus d squared. Alright, okay. Now let's plot this complex number on the argand diagram. This is the real part, or the real axis, and this is the imaginary axis. So you're going to get a, b. So this part is going to be a comma b. Alright, now we can join a line from the origin to where we have the plot of that particular complex number. So here, so that line that's join the origin and this particular point is what we call the what? We call the modulus of the complex number, and it is written as R. So the reason why we had square root of the real part squared plus the imaginary part is this is going to form a right angle triangle, and the modulus, or this part, will form the what? Will form the hypotenuse of the what? Of the right angle triangle here. So by Pythagoras theorem, we are going to get R equals square root of a squared plus b squared. Alright, so the R, which is the what? The modulus of z, is going to be square root of a squared plus b squared. And now, so that's how we find the modulus of a complex number. All that you have to do is to take the square root of the real part squared plus the imaginary part squared. Alright, let's move on to the argument of a complex number. Argument of a complex number. Alright, the argument of a complex number is the angle between the positive real axis and the line representing the complex number on the argand diagram, or is the angle between the positive real axis, and the modulus of the complex number, or the argand diagram. So let me use the complex number z equals a plus bi again here. So here the imaginary part, or the imaginary axis, real axis, we're going to have a, b. Okay, so this is the modulus of z, right? So this angle here is what we call the what? The argument, because it is the angle between the modulus, or the line representing the complex number, and the what? And the positive real axis. This is the positive real axis. So this angle, the angle between these two lines, the modulus and the positive real axis, forms the what? The argument. So the argument here is what? The theta in between the real axis, positive real axis, and the what? And the modulus. Right. So in most books, you will see something like argument of z, arg z. This represents the argument of that particular what? Complex number. Alright. Now let's move on to the principal value of the argument. The principal value of the argument. So this is the argument, and let's move on to the principal value of the argument. Now the principal value of an argument is the value which lies between negative 180 and 180 degrees. So what it means is that when we have an argument and we want the principal value of that particular argument, it should fall within this range. It shouldn't go beyond negative 180 or beyond positive 180. So you cannot have a principal argument of 181 degrees. No, it's not right. So it should be between this range. Okay. Now let's represent the principal value of argument in each quadrant of the argand diagram. Let's start with the first quadrant. We are still using our z equals a plus bi. This is the real part, and this is the imaginary part. This is our a part, this is our b. That's the imaginary part of the complex number. So at the end of the day, we are going to get a comma b, with this being our what? Our modulus. Alright. And here is going to be what? Let's say alpha. Alright, now this is a right angle triangle, like I said. So let's compute the value for alpha. So we can use the trig functions. So here you can use tan. So tan alpha is going to be opposite. That is b over a, right? Opposite over what? Adjacent. So alpha will be equal to tan inverse of the absolute value. Always the angle should be positive of b over a. So this is what alpha will give us. Now we are saying that for the principal value of the argument, it should lie between negative 180 and 180. So in the first quadrant, there is no way that the angle is going to go beyond 180, because the positive quadrant here, the imaginary part is positive and the real part is positive. So let's focus on the 180 here. There is no way that alpha is going to go beyond 180, right? Even if the maximum value of alpha that we can get in the first quadrant is 90. So here we can simply say that the argument of z is going to be what? Alpha. Because it satisfies the what? It satisfies this condition. It lies between negative 180 and what? 180. So in the first quadrant, the argument is just the angle that you find there. You do nothing to it. So it will be just the angle over there like this. So here the argument of z is just equal to alpha. I hope I'm clear. If I'm clear, then let's move on to the second quadrant. Second quadrant. Still using z equals a plus bi. Now this is the second quadrant. So here we are going to have negative real axis here, positive imaginary axis. This is the real part A. This is the imaginary part B. So the z is supposed to be negative a plus bi, because in the second quadrant, the real part is what? Negative, and the imaginary part is positive. So this is what you are going to get. And always the angle should be between the what? The positive, the real axis and the what? And the modulus. The angle, that's just the modulus, but the principal modulus or the principal value, the angle should be between the real axis and the modulus, but the principal value of the argument should be between the positive real axis and the modulus, right? So always the angle. In the Cartesian plane, we can say it's always taken with respect to the positive x-axis. So here, it is taken with respect to the real axis like this. So this is the angle, right? So let's say this is alpha. And what did we say about the principal value of the argument? We said the principal value of the argument should be between the positive real axis. This is the positive real axis. So it should be between the positive real axis and the what? And the modulus, like this. So here you can say this is what? Theta. So this theta here, this theta is the actual what? The actual principal value of argument, right? Because here, although we have an angle alpha, which is between the negative real axis and the modulus, but that's not what we are interested in. We want the principal value of the argument, and that should be between the what? The positive real axis and the what? And the modulus. And it should also satisfy this condition. It should be between this range, negative 180 and 180, right? So before we can find this theta, or let's say, how are we going to find this theta? The whole of the angle here, angle on this axis, the real axis is what? 180. We want to find what? This theta. So theta is going to be what? Theta is going to be what? 180 minus alpha, right? Theta is going to be 180 minus alpha. And what is alpha? Alpha is going to be tan inverse of the absolute value of what? B over A. The reason why I didn't bring the negative is because it is in the absolute what sign. So the argument of z, which equals theta, will be equal to 180 minus alpha. So we have 180 and we are subtracting something from it. So there is no way to go beyond 180, the negative 180 or positive 180. It will fall within the range. So in the second quadrant, the argument, that's the principal argument of z, is going to be 180 minus the angle here, which is alpha in this case. Are we good? When we solve examples, we will understand better. Let's move on to the third quadrant. So in the third quadrant, everything is negative. So negative a, negative bi. This is what you are going to get in the third quadrant, because here is the negative real axis and here is the negative what imaginary axis, and we have alpha here. So the alpha here represents the what? The argument, right? But we want the principal value of the argument. The principal value of the argument is the angle between the positive real axis, this axis, and the what? And the modulus. So if we are taking it from this direction, if we go this direction, so here is what? 90 plus another 90, making what? 180 plus alpha. So we have 180 plus alpha, but the condition is that it should be between negative 180 and what? 180. But here is the case that if we are saying the real axis, the angle between the real axis and the modulus is taken in this direction, it's going to go beyond that, because we have 180 plus alpha, which is going to be more than 180. So what are we going to do? So in the third quadrant, we don't take the angle, or we don't measure the angle in the what? In the anti-clockwise direction, but rather we measure it in the what? In the clockwise direction. So in this case, this is the real axis, so we can measure it from here. When we measure it from here to here, we're going to get our what? Theta. And mind you, when you are measuring angles in the clockwise direction, you're going to have negative angles, right? So here, you can say the argument of z, which equals theta. Here, this is the principal value of the argument. Is going to be equal to what? Negative 180 minus negative alpha. So the argz, which equals theta, is going to be negative 180 plus what? Alpha. Because here the whole of the angle here is 180, and if we want this theta, we have to subtract the theta, the alpha, from the 180, right? And here the 180 is measured negative because we are going in the what? Clockwise direction. So is the alpha. So all angles measured in the clockwise direction are what? Negative. Okay. So argument of z here is going to be negative 180 minus negative alpha. So you're going to get negative 180 plus what? Alpha. So this is what happens in the third quadrant when we are finding the principal value of the what? Of the argument. Alright, let's move on to the fourth quadrant. In the fourth quadrant, z will be equal to positive a minus bi. This is the fourth quadrant. Here is alpha. Here is positive real axis, and here is what? Negative imaginary axis. Here is going to be our what? Our b, and here is going to be our what? Our a, right? Okay. So let's see if we are going to find our argument of z. Our axis is going to be what? Here, the principal value of the argument is taken from the positive real axis. This is the positive real axis, right? This is the positive real axis to the what? To the modulus, the angle between them, and here is the angle between them. Now, if we are supposed to take it in this direction from here up to here, we would satisfy this condition. So better we take it in the what? In the clockwise direction. That's why we are taking it in the what? In the clockwise direction. Alright, now so when you take it in the clockwise direction, you're going to get what? This distance from here up to here, which is what? Alpha. But we were measuring it in the what? In the clockwise direction. So the axis is going to be negative what? Alpha. It's going to be negative alpha. Right. So that is that for the representation of the what? The principal value of the arguments in the various quadrants. So here the alpha is going to be the tan inverse the absolute value of what? B over A, using what? The trigger identities to opposite over adjacent. This is what you're going to get. Right. Now let's solve some examples and see if you're going to have a full understanding of the modulus and the argument. We are supposed to find the modulus and the principal arguments of this complex number z equals 1 minus I. We are finding the modulus and the principal argument of this complex number. Alright, now let's start solving. Okay, so what did we say the modulus is going to be? So the modulus of z, which is the absolute value of z, is going to be what? The square root of what? The real part squared. Here the real part is 1. So 1 squared plus the imaginary part, which is what? Negative 1 squared. And when you compute this, you are going to get square root of what? 2. So this is the modulus. Let's move on to the principal argument. Now let's draw the argand diagram for this. So this is the real axis and this is the imaginary axis. We have positive real axis and negative imaginary axis. So we are going to which quadrant? We are going to the what? The fourth quadrant. So we are coming here. Here is going to be 1. Here is going to be what? Negative 1. We are going to have our angle here. Alright. Now let's find the alpha. So tan alpha is going to be the absolute value of what? Negative 1. That's this part to our opposite, which is negative 1 over what? Adjacent, which is 1. Absolute value. So alpha is going to be tan inverse of what? Positive 1, which equals what? 45 degrees, right? Okay. But here we are saying we want the principal value of the argument. So it should be taken from what? In the third quadrant, we said the argument is going to be what? That's the negative of the what? The negative of alpha. So in this case, arg z is going to be negative what? 45 degrees. So here we can say that we have the modulus of what? Square root of 2, then the argument of what? 45 degrees. Let's move on to another example. Z equals 2 plus I. Z equals 2 plus I. Now, absolute value of Z, which is the modulus of Z, is going to be square root of what? 2 squared plus 1 squared. So, modulus of Z is going to be square root of what? 5. Alright, now let's draw the argand diagram and find the argument. Okay, so we have positive, positive. So it will lie in the first quadrant. So here is 2, here is 1. We're going to have something like this. So 2, 1. We have this here. This is going to be alpha. Right? Let's find alpha. Alpha equals tan inverse of the absolute value of 1 over 2. So alpha is going to be 26.256 degrees. But in the first quadrant, we said the argument of z is going to be what? Just alpha. So here, argument of z is going to be 26.256 degrees. So we can say for this particular complex number, the modulus is square root of 5 and the argument is 26.256 degrees. Let's move on to the third example. Z equals 1. We are supposed to find the modulus and the argument of this complex number. Z equals 1. How are we going to do it? Now, which means here, this complex number has no imaginary part. So I can rewrite this as z equals 1 plus 0i, right? So finding the the modulus, you're going to get square root of 1 squared plus 0 squared. And when you compute this, you're going to get 1. Let's draw this on the argand diagram. So we have only the real part. The imaginary part is 0. So here is my 1. And here is my 0 for the imaginary part. So here, the modulus is going to lie on the on the positive real axis like this. Because there is no angle between it. This here, there will be no angle between it. Is that okay? So you are going to get the argument of z as just 0 degrees. Are we okay? Because here the imaginary part is 0. If it were to be maybe positive, you would have come up here and you would have joined the line like this, from here to here like this, or you should have been somewhere here. You would have joined the line to get something like this. But it is here, so if you join the line, it's going to fall on the going to fall on the positive real axis. So here there will be no angle between the positive real axis and the and the modulus, since the modulus is falling on the on the positive real axis. Let me draw the argand diagram again. This is the real axis. And the real part is 1. And the imaginary part is 0. So this is the imaginary part. So here 0, 1. This is where the plot is going to be. And if I join from the origin to where the plot is, it will pass through the imaginary, the real part, the line of the real part, or the positive real axis. So I'm going to have 0 angle between them. Therefore, we are going to get argument of z as 0. So here we can say that this complex number has coming. So this complex number is having a modulus of 1, an angle of 0 degrees. Alright, let's solve last example. We are finding the argument and the modulus of this complex number I. So here we only have one imaginary part, or we only have an imaginary part, no real part. So you can rewrite this as 0 plus I, which means that real part is 0. So here, if we are taking the modulus, you're going to have square root of 0 squared plus 1, which is going to give us 1. Plotting this on the argand diagram, you're going to have something like this. Okay, so here the imaginary part is 1, and the real part is 0. So here it's going to lie here. What to be the angle between the positive real axis and the modulus? Because here the modulus will lie on the imaginary axis here. So the angle between the real part, the positive real axis, and the imaginary part, or the modulus, is going to be this angle, which is 90 degrees. So by inspection, you have to be able to draw out your angle from the argand diagram when you have questions like this. So here it's obvious that we are going to have a complex number with 1 as the what? As the modulus, and what? 90 degrees as the what? As the argument, or the principal value of the argument. So that is that for the principal value of argument, modulus, and the argument of a complex number.